Okay, so to clarify what functional morphology is, we have to start with a description of morphology. So what is that? What does that word mean? And what that is it's the observable characters that you can deduce from looking at even just a fossil, or you could look at a living organism and describe its morphology by noting the color, the pattern, the shape, the size, the symmetry of those observable features. So that's morphology. And what functional morphology is studying the relationship between that structure that you've observed and the function of those structural pieces. And today we're going to do something exciting. So we're going to try to figure out how marine organisms or marine invertebrates lived even millions and millions of years ago. So we can deduce that information from looking at a marine fossil. That's pretty amazing, I think. So what we can infer from looking at a fossil is how that organism lived. So this is the lifestyle of that organism. So again, I mentioned we're referring to marine invertebrates for today. And so we're going to be thinking about the water column. Okay, so think about if you've been swimming in the ocean or maybe the pool as an analogy, if you will. So the two areas that an organism could live in the ocean or a lake or a river, the two regions are the pelagic region, which is the open water, so sort of up in the water, maybe swimming around. We'll talk about that in a minute. So up in the water column is called the pelagic region. If an organism lives along the seafloor, that's called the benthic region. So it's a benthic organism. So just to reiterate, in the water column, that's a pelagic organism. If it's living along or near the seafloor, that's a benthic organism. Within the pelagic region, so if you've identified that the organism lives in the water column, you can start to think about how that organism moved. So could it move? So for example, if you have ever seen a jellyfish or you've identified a soft, squishy, well-preserved jellyfish, a fossilized jellyfish, you would notice that it has radial symmetry. So what you can deduce from that information is that it wasn't necessarily moving in any particular direction. And so from that, you can infer that a jellyfish is a planktonic organism. So it's sort of, the definition of a planktonic organism is that it lives in the pelagic region and it kind of floats with the current. So it's not necessarily moving in a particular direction, but it's at the mercy, if you will, of the currents and is sort of not moving in a particular direction. So that's what you want to keep in mind if you have identified a radially symmetrical organism, is that it's not moving in a particular direction, so it could be planktonic. A jellyfish is a great example of that. So to contrast that, we have nectonic organisms. So a shark, ooh, definitely nectonic. And how you can identify that an organism is a nectonic organism is that maybe it is, it's usually, I should say, bilaterally symmetrical. So it seems to have a head and a tail. In a shark's case, it's very streamlined. It looks like it can move really easily in that particular case. And so a nectonic organism can swim in a particular direction. So it's actively swimming in a direction versus a planktonic organism which floats with the current. So if we can move from our pelagic area down to our benthic region, along the seafloor here. So this is where it gets a little muddy. Oh, no pun intended. Yes, okay. So in the benthic region, what you want to consider first, I would say, is if the organism could easily bury itself. So if we think of a spiny conch, for example, one of our gastropods, like I said, it's spiny, so it has all these projections. So you could think about it living on the seafloor, so it has kind of that flat bottom side, if you will, so it easily could move along the seafloor, but then it has all the spines kind of curling up off of that beautiful spiral shell. So first you would identify that it's benthic, it has that flat bottom, so it can move along the bottom of the seafloor, but you are starting to identify that maybe it couldn't bury itself in the sand, in the actual seafloor, in that sediment very easily. So if it's not really streamlined, and it has these spines like the conch, you would call that organism, or you would hypothesize that that organism is an epifaunal organism. Okay, I know this is a lot of terminology, but you just got to learn it so you can apply it to these different fossils and these different invertebrates that you're going to be considering. So our conch is a great example of an organism that moves along the seafloor and is epifaunal. So it's projecting, or it lives on top of that seafloor. In contrast, there are infaunal organisms. So infaunal refers to those organisms that look like they could easily bury themselves. So they can kind of squish under the mud or dig down and live within the seafloor. And those organisms are called infaunal benthic organisms. Okay, so we have a lot of adjectives here, so we'll try to keep them straight. So once you've established if an organism is epifaunal or infaunal, what I'd like you to think about is if that organism could move. Okay, so you, for example, are a vagrant organism. All right, so our term that you would apply to an organism that looks like it can actively move is vagrant, okay? In contrast, we want to use the term sessile. So sometimes on a Saturday, you might be sessile on your couch. So you're not moving. So the term sessile refers to organisms that, yes, they live on the seafloor. Maybe they're epifaunal, so they're maybe like a crinoid, okay, living on their little segmented stalk. But like I said, it's on a stalk, so that organism is not likely to be moving around on the seafloor. So we would call that organism, here's all your adjectives, a sessile organism. It's epifaunal, and it's benthic, okay? So we can be really specific about how we describe these fossils and their lifestyle. So that's great. We can apply all these terms. I know you're really excited. Apply all these new terms to our marine invertebrates and other fossils that you run across.